All right, welcome back. So we left off this conversation talking about ice cores and the similarities between ice cores and the soil sample cores that we take, and we will take in Earth and Environmental Science hopefully next year. But anyways, keep going though. So we can actually analyze the air trapped in the ice to learn how the atmosphere has changed over time. It can tell us the temperature, volcanic activity, if there is like ash or dust in there. It can tell us the composition of the air as far as makeup. Like we know today, our atmosphere is mostly nitrogen, 78%, and 21%, of oxygen. Maybe it differed over time, and it most likely did. So that is pretty awesome. Ice cores are really cool ways to kind of see and track the changes of life in the environment. But we're going to keep going, so we're not going to stop and think. We're going to keep going again and talk about what does sedimentary rock tell us about the Earth's past. This is pretty cool. So sedimentary rock can tell us the relative age. The relative age is the age of an event or object in relation to other events or objects, relative. In the past, fossils, rocks, etc. were used to reconstruct the Earth's past or our understanding of Earth's history. We didn't have technology. Now we do. Now we call this absolute dating, and we're going to have a whole lecture on that, and we'll actually have a whole lecture on relative dating, but this is kind of a brief overview of where we'll go in the next couple of days. So sedimentary rock forms in layers. We know that. That's what makes sedimentary rock distinguishable between that and metamorphic rocks and igneous rocks. It's layer upon layer of sediment stacked and compressed together and cemented. That's how a sedimentary rock forms. So we've got this law. It's called the law of superposition, and it says that each rock layer is younger than the one below it. So with this idea, the oldest layer would be at the bottom. Think about it. If a sedimentary rock is sediments compacted and cemented, so pushed together and cemented, then you would assume that as the sediments pile and pile and pile, you're going to get different layers. Meaning if the oldest is on the bottom, the youngest is on the top. We call this, again, the law of superposition, and we will talk about it another day, specifically on Thursday and Friday. But we call this relative age because we don't know exactly when each layer is formed, but we do know that the bottom one is older than the top one. So that's why it's relative. How can rock layers be distributed? By the way, I expect you to highlight relative age and that the oldest layer is on top and the youngest is on the bottom, and the law of superposition. How can rock layers be distributed? This is where your notes pick back up as far as filling in the blank. So be ready for that. The movement of tectonic plates can change the way that rock layers are distributed. A whole set of layers can get turned on its side. It can be bent or folded to where the oldest layer is no longer on the bottom. We call this unconformity. And again, we'll talk about this another day in depth as well. One way we determine the original order is by looking at similar stacks of undisturbed rock. So if there was an area that the tectonic plates had moved, we could look at its surrounding area and see, okay, were those layers undisturbed or not? Another way that our rock layers can be disturbed is by igneous rock coming in and moving the other rock layers. So a molten rock or magma can force its way through our sedimentary layers. When the magma cools, it forms igneous rocks, but the problem is it's disturbing our sedimentary rocks. It can even look like just a big pile of, not a big pile, but a big splotch of igneous rock going right through our nice fine layers. The igneous rock is always younger than the layer it cuts through. Think about it. The rocks have to be present before the magma can cut through them. Okay. What are index fossils? So these are fossils in sedimentary rock that can offer clues to Earth's past. Our fossils can tell the age of a rock. If the organism lived when the rock layer was formed, then that gives us an idea that the rock was formed then. An index fossil are common fossils of common organisms that lived in many areas during a specific span of time. They're used to determine age of a rock layer. For example, a type of shellfish Labiatus lived from 144 million years ago to 65 million years ago. So if you find its fossil, you know that the rock layer is between 144 and 65 million years old. But again, it's relative, and these aren't exact sciences like our absolute dating, so it's just a pretty basic, good, educated guess of when that rock was formed, but it's not absolute. Just a little bit more. Here's how we tell our absolute dating. We find the absolute age, or the actual age of an object or event. It's determined through radioactive dating. We do this because we know the half-life of an organism. A half-life is the time it takes for half of the atoms in a radioactive sample to break down. Different elements have different half-lives. Specifically, scientists will use uranium and carbon-14 to date rocks because they have long half-lives. Carbon-14's half-life is 5,730 years. Uranium's half-life is 704 years. Radioactive dating works best for igneous rocks. Also, you cannot do this on a sedimentary rock because if you think a sedimentary rock is a rock that has tiny bits of other rocks in it. So it's really just a bunch of tiny rocks squished together and cemented. So if I take a radioactive date of a rock, it's not the same throughout. So the date of a the age of sedimentary rock isn't going to come out right if we absolute date it. This works best with igneous rocks. It can work with metamorphic rocks, but we almost need all of the same substance. So a metamorphic rock isn't all of the same substance necessarily always as far as elements go, but an igneous rock is all the elements kind of melted together like a melting pot. So think if you were melting crayons, for example. I used to melt crayons when I was younger. You could make like colored crayons. If I just shaved up the crayon bits and then I took my hands and I smushed them together, that would be a sedimentary rock. If I shaved up the crayon bits and I heated them just a little bit and got them kind of goopy like Play-Doh, and then I pushed them together, that would be an igneous rock, but you could still see all the distinct colors of the crayons. Or sorry, that would be a metamorphic rock if I heated them just a little bit and mushed them together. And I could see each distinct color still, kind of like a splotch. That would be a metamorphic rock. If by chance, though, I heated up my crayons all the way till it was like a soup and I could stir it and then let it cool, that would be an igneous rock. Okay? So you need all of the different pieces of rock, because all rocks are just rocks, continuously recycled in the rock cycle, but you need that rock to be one complete substance. It can't be the little bits and pieces mushed together like with metamorphic or sedimentary rocks. So this works best with igneous rocks. There we go. Rocks that were once magma or lava and then cooled to become a rock, like obsidian. And this, my wonderful students, is the end of our lecture on fossils. Now, when we talk about our absolute dating, which will be Thursday and Friday, a lot of this is going to sound familiar. So we're going to go over this again just a little bit and look at it in a different way on Thursday and Friday. Wednesday this week, we will be doing absolute dating, so we'll have a whole lecture on this slide right here. Awesome. Have a fantastic day, and I hope you enjoyed the video lecture.